Today we will see some topics on mm, week 6. So week 6 comprises of two main topics. One is the Routh-Hurwitz criterion to find the stability of a system, and the second one is root locus. First, we'll start off with Routh-Hurwitz criterion. We have seen some examples based on it. Now we'll see all the rules that satisfies this condition. What are all the special cases that exist in this condition? We'll just quickly go through this. If you have any doubt, you can ask. Otherwise, I'll quickly go through this. So when you see the lectures, it will be helpful for you.
Yes.
Okay, right. So Routh-Hurwitz criterion is primarily developed to find the stability of a system, of any system. One advantage here is usually how we find the stability of a system. We look for its location of poles, right? When the location of poles is in the left half of, we'll just say it is stable. If it is in the right half of the S-plane, that will be unstable. Even one pole that lies in the right half of the S-plane makes the system unstable. It will create unnecessary exponential behavior in the output response that makes the system unstable. Okay, so till now we have seen where the location of, where the poles are lying around in a system by using a characteristic equation that is that will be equated to 0. Out of this we will find the roots, so that roots tells the poles of the system. This is possible until it reaches s power 3. So for a third order system this is possible. Until third order system this is possible, first, second and third. After it reaches s power 4, it's very difficult to use this method to find the location of poles. You must need some MATLAB or calculator's help to go beyond this. So at this point, when there is no computer based or sorry, MATLAB based or any mathematical tools available, so you should depend on some other techniques. That technique is the Routh-Hurwitz criterion techniques. Even we can go up to s power 8. There is no other physical system that has s power 8 that much complexity, but for mathematical analysis we can go more beyond that, not restricted to even 8. So this method helps you finding your location of poles for higher order systems. How can we do that? There are some steps where the method explains. If you have a characteristic equation like this, characteristic equation is the denominator of a transfer. So if you have a transfer function b of s by a of s, this a of s will be equal to 0, that it is called as characteristic equation. So from this, usually we will get roots if it is a s cube until s cube. But for higher order system, we are going to use the same technique. So considering this as your characteristic equation, the method is to first start with your higher degree polynomial, whatever your higher like last degree of that polynomial, even if it is s5 or s6, whatever it is starting from, start with that. Then write the odd number of coefficients of odd degree polynomials in the first row. Let me write it somewhere else. Okay. Okay. The first row, oh, first row should be coefficient of odd degree polynomial. Second row should be coefficient of even row polynomial. This is the first step you have to follow. If this is your characteristic equation, let me write it. I am assuming this is the odd degree polynomial. That's n starts with, let's take n equal to 5. Okay, so let me write from s power 5, then its coefficient an. This is the coefficient of the higher order polynomial, right? An. Then I will skip this because if this is odd, the next one will be even. For example, s power 4. So I'm going to skip it and I'm going to write the coefficient of s power 3 here. Then s power 3 would be an minus 2. Then I'm going to skip 2 again and I'm going to write the coefficient of s power 1. That would be a n minus 4. Then no other odd polynomials left. That's it, right? Then I'm going to write in the second row, I'm going to write the polynomials coefficients of the even order polynomials. That would be s power 4, s power 2, and s power 0. Right? S power 0 should also be included. Okay, this much I have. This is the first step. The second step is that I have this, I'm just rewriting it here. Okay, this corresponds to s power 5, s power 3, s power 1. This is s power 2, s power 4, s power 2, s power 0. Okay, now we have to find the row for all this equation until s power 0. Whatever polynomial you have started, you have to write the rows for all this equation. How you can write this row? The first thing you should do is take the lower second row and multiply it with this upper row's second element. So this will give you an minus 1 into an minus 2 minus, this minus is very important, and then take the first row's first element and second row's second element, kind of x this direction you have to multiply. First multiply this two element, subtract and multiply this two element, put it here, an into an minus 3 divided by wherever you have started. This is the first element you have started, right? That element you have to write in the middle. Now here this will be an minus 1 into an minus 2 minus of an into an minus 3 divided by an minus 1. This should be this third row's first element. This entire thing is the third row's first element. I hope this is clear. Similarly, you have to do for this also. First multiply this, subtract, multiply this, divided by an minus 3. This element would be an minus 3 into an minus 4 minus an minus 2 into an minus 5 divided by an minus 3. Right? Similarly, you have to follow the same method until you reaches only one element for s power 0. This is the second rule. There are only two rules for this. Okay, once you reaches this entire row, you have to look for any sign change. For example, if I have 5, 7, some 9, 10, 1, again 8. Okay, there isn't any sign change, right? Sign change in the sense anything change from positive to negative. Only the first column you have to check always. No need of any other columns. The first column after this polynomial representation, you have to check, is there any sign change? If important point here is, if there is any sign change, the system is unstable. For a stable system, there should not be any sign change. everything should be either positive or everything should be either negative. There should not be any change in between the positive to negative or negative to positive. Right. And again, another sub criteria is that number of sign change is equal to number of poles in RHS. So if you have sign change, then the system is unstable. So if someone asks how many, okay, and it is unstable, there must be some poles in the right half of the S plate. I want to know how many poles are there in the right half of the S plate. So you can say it with the number of sign change happen. For example, if there is a minus here, so there is only one sign change happened here, right? uh, Sorry, two sign change happened here, positive to negative, negative to positive. Then there are two poles in the right half of the SP. Excuse me, 2 minutes. Sorry. Okay. Is that clear right now until this
Oh,
point?
yes. Yes, ma'am. Ma'am, one question I want to ask.
Yeah. Yeah.
Ma'am, what is the idea behind like this formula that we are doing?
Okay. Just idea in the sense we couldn't use any method to find the stability of a system if it goes higher order polynomial, right? So we are like we checked in normal second order polynomial. Let's take a square plus bs plus c equal to 0. So here we will see all the coefficients of this should be positive, right? So that you will get poles that are in the left half of the x plane. This will be the roots of the system will be s plus a, s minus s or s plus b. So this will be s equal to minus a is equal to minus b. If there is one sign change, then one of these roots should be s minus a into s plus b to accommodate those polynomial, then this will push one root to the right of the s plane. So similar to this, in this method also we are looking for any sign change. If there is any there isn't any change, sign change, all the poles are in the left half of the s plane, so the system is inherently stable. That's what the idea behind this is.
Like we are multiplying roots and then subtracting, like kind of finding determinant. Why are we doing that? Like how does it help?
Oh, okay. mm, okay, how this will help? Right. Uh, I couldn't answer this question. I can think and tell you.
We are making a table for all the coefficients and taking out one by one.
Yeah.
Like how is coefficient doing this thing helping?
Right. I got your question. I couldn't answer it right now. I can prepare and tell you. The main idea behind this is this: you are looking for whether any coefficients of any of the coefficients of the higher order polynomial is being changed. But why are we doing this particular mathematical um, like multiplication and subtraction? I can answer you in the next class probably. Is it fine?
Yes, ma'am.
Okay, right. I'll keep that in mind. Okay. Right. Um. Okay, fine. So far we have been seeing if there is no sign change, then the system is stable. If there is any sign change, it is unstable. And the number of times the sign change is equal to the number of poles that has been lying in the right of the S plane. Okay, there are some special case. Something if something happens, how we can tackle those. The first special case is that getting a zero in the first column. When we are doing the mathematical operation, sometimes you will get similar coefficients of the polynomials, and you might get zero in the first column of the equation. Then you cannot proceed with the next steps. Whatever you are multiplying it with, it will give you zero. So sometimes you cannot identify the coefficients beyond this level. So what we can do is, for this special case, this author who found this problem has come up with a solution that just replace this zero with a small probable value, very small, 0.000 something, very small probable value called as epsilon, and keep that as a variable, and then you look for the sign change. Do the same operation until you get to s power 0, and then look for the sign change. Just a simple replacement of 0 with a very small integer epsilon. So here if you see 1 if you multiply this 2 minus 2 divided by 1, this will be 0. So we are replacing the 0 with the epsilon here, and then we are proceeding to do the same multiplication operation. 2 minus 2 divided by 1, that will be replaced by epsilon, and here 6 minus 30 divided by 2, that will give you minus 12. Then in the next step you are proceed to the second operation. Let me show you here. 2 epsilon, this will give you 2 epsilon minus minus of minus 12, so plus 12 divided by epsilon. That's why here you have 2 epsilon plus 12 by epsilon. Similarly, you do this. See, if one element is not there, that you can neglect. Here, consider it as 0. That's it. So this will become minus 12 into 15 minus 0 divided by minus 12. Then it will give you 15. Okay. Similarly, you are doing operation for this, considering this as 0, and this and this. Right? You have to replace the 0 with epsilon only in the first row of the column if it exists in the first column of the row table. Good. Now you look for the sign change. So when you see here, this until this point it is positive, but here it is a whole negative for the whole equation, upper numerator and then denominator, not just for only 15. So here there happened a sign change, so you can straight away tell the system is unstable. If this is positive, then you can say the system is stable if there is any sign change. This is one first one case of the Routh criterion table. And the next case would be, what if both the rows are 0? Can we replace both with epsilon epsilon? Then if you do so, again it will give us same problem only. Again the next row will also be 0. So instead of doing this, they are coming up with another one point. How you can tackle this problem is that just look the row above that row where it went 0. So this row's coefficient is 50, sorry, 5 and 30, right? Just write this coefficient as a auxiliary equation, right? If you write it in terms of auxiliary equation, you will get a new characteristic equation. How can we write it in terms of auxiliary equation is that look for the coefficient, sorry, polynomial here in the left of that particular row that starts with s square, right? So I'm going to write it as 5s square plus 30 equal to 0. It's an even row. There won't be any s. So s 5s square plus 30 equal to 0. This is your auxiliary equation. Once you get this auxiliary equation, just write it in terms of A. Just name this equation as A and differentiate it with respect to S. The only variable that is there in this equation is S, right? So differentiate it with respect to S. This will give you 10S. This will give you 10S, right? So use this coefficient in the second row instead of 0. This can be 0. No need of replacing this second one. It's like if it is not there, how it will be. You have to consider it like, excuse me. Okay. Right. So replace this here. Replace this 10 here. And then you can proceed with the normal method how we used to follow. So so far we have seen how to, in general case, how to write the how to find the stability, and in case 1, what if first element of the column goes to 0. Case 2 tells all elements goes to 0. In case 1, you will just replace the 0 with epsilon. In case 2, you will write an auxiliary equation and derive it, differentiate it with respect to the s. So auxiliary equation can be written based on the previous rows. So then you will replace that with the coefficient that has been 0. No need to replace the second row. If there is a auxiliary equation, if in that auxiliary equation, if there is a coefficient, for example, s power 3 into s power 1, in that case, if you get a coefficient, that's fine. Otherwise, you can just replace whatever is there in the auxiliary derived differentiated form of the auxiliary equation. Right. There exists some other case, another case where you get similar to that, you get the all rows 0 here. We are doing the case 2 method here. So the previous row has the higher polynomial as s power 4. So 2s power 4 plus 4s square plus 2 equal to 0. Then they have taken out the common coefficients. Then it becomes 1, 2, 1. So if you differentiate this, you will have this kind of equation, right? They're replacing it to this second equation and finding this. And I forgot to tell one thing here. So when you find the auxiliary equation, the stability of the system depends on auxiliary equations root. If you find the roots for this auxiliary equation, then it will be s square plus 6 right? So this will become s is equal to 2 root 3 or root of 2 root 6 maybe. Root 6 plus or minus root 6 it will be. So it is a complex pole pair. It is not a single pole, it's a complex pole pair. It has this plus minus root 6 and plus root 6. So this is again a problem, but you can conclude. Oh, I'm sorry. It's a pole pair, but in the imaginary axis, right? Only I will be there. So root 6 and minus root. So this is a complex pole pair that lies straight in the imaginary axis. Whenever a pole is there in the imaginary axis, we won't tell whether it is a stable or unstable. We'll just mark it as a marginally stable, right? So in this case, it will be marginally stable. Whatever the whether there is a sign change is there or not, it will be marginally stable. Since we use the auxiliary equation, the stability depends on the nature of the auxiliary equation. So here also you are,
Ma'am,
yeah.
ma'am, can you give one example of this quadrantal pole?
One example of this.
Quadrantal pole, like some equation having
Ah,
quadrantal pole.
yeah, this is the equation, right? 5s square plus 30. So when you take this 5s square plus 30 equal to 0, this is the auxiliary equation. So this will be 5 will be out. So this will s square plus 6 equal to 0. Will give you a square equal to minus 6. X is equal to plus or minus 6i, because there is a negative sign here, right? So it will be a complex number. So plus or minus root 6i lies in the imaginary axis, not inside or outside the, sorry, not in the LHS or RHS, right? So this will become a marginally stable problem. Uh, is it okay? This example
Asking like this third
does.
one, where there are four poles
I'm
in
coming
that
to that.
line.
Yeah, yeah, I'm coming to. Okay, right. So this is a case of one single pole pair. One single pole pair, until it has one single pole pair, that is fine. But in this case, if you see, the auxiliary has pole pairs. For example, there are two poles in minus 1 plus 1 j and two poles in the minus 1 j, right? So this will make the system unstable. Why it is making a system unstable means, if there exists two poles that lies in the same place, if it is in the LHS, that is not a problem. For example, here in this LHS, that is not a problem. It is not going to make any issue. But the poles that are repeated in the or on the imaginary axis will create a problem, because it interferes with the frequency of the system. So that itself, since it is marginally stable, the single pole pair itself is oscillating. So if you add the frequency to that, furthermore, that might push the system to the unstable behavior more likely. So whenever there is a more than one pole pair lies on the imaginary axis, for example at the same frequency, then the system is unstable. We will call that system as a unstable system instead of marginally stable system. So here, how do we find it? Like here, so S cube, when you used to find the, sorry, okay, a square plus 0 is a s cube plus 0 x square plus bs plus 0 equal to 0. So when you find that L type equation, how will you find this coefficient a 0 b 0? So you use minus 1 and all to find those roots of this equation, right? When you use this equation, you will find a pole pair instead of a pole, that is plus or minus j twice. So this creates an issue in a system. So the system, instead of one pole pair, if there are more than one pole pair lies at the same location, it's become more oscillatory. That will make the system to go from marginally stable to unstable more likely. So the system is called as unstable that from that time itself. Is it clear?
Yes, ma'am, this is clear. But ma'am, that third image uh, in the three cases,
Ah,
that one is having like these four poles in all the four quadrants.
yeah.
Like some example for that. How
Okay.
can we have four quadrant poles?
Oh, you are asking this.
It's from this third figure where we are having
um,
four poles in each quadrant.
Here, this one.
No, ma'am, this is clear. Like there are two poles on the same point, but in that image, there are
Can you
one
see
pole in
tell
each
the
point.
page number?
On this only, special case auxiliary polynomial. In
S-
this, yes, this slide only.
Special. Oh, this slide.
Yes, there are the third case. Roots are quadrant about the two axes of the S plane.
Okay. Actually, it is not quadrant, right? Oh, here. Oh, this case you are asking.
Yes, ma'am.
Okay, this is like a unstable system only. It's an example. That's it. Two pole pairs are in one pole pair is in the left half of this plane, another pole pair is in the right half of this plane. Just these are all one pole pair and these are another pole pair. This is like 2 plus or minus 3j minus 2 plus or minus 3j. Whenever there involves any right hand side visibly, it's an unstable system. That's it.
Yeah, okay, ma'am, got it.
No need to check. Similarly, this system, right? So this will be unstable. This will be unstable. But here, two are in the two are on the imaginary axis. So it is marginally stable for now until it has only one pole pairs. If there is another pole pair sitting at the same location, for example, it can have this pole pairs. There are some other pole pairs that can be at the different location. That won't make the system unstable. But if more than one pole pair lies on the same location on the imaginary axis, then it is unstable.
Yes, ma'am.
Right. Okay. Good. So this is one big topic we have covered for the exam.
Now I have in this lecture in fourth slide.
The same lecture.
Yes, ma'am.
Fourth slide. Ah.
Uh, this ratio equation that we have find, the first
Mm-hmm.
equation, like how are we getting this that I got by dividing two equations? But both of them are all like same only. So why are we finding this ratio? I didn't get.
Ratio. What ratio?
Like it can be shown that the equation that it is in the first part, all the ratios should be non-negative. Why are you finding these ratios?
Roots of the characters equation lie if necessary. The all questions are non negative. Okay. Have same sign. General properties, right? An equal to minus pi. Okay, right. But these conditions are not sufficient. Roots of the equation are at s power minus 2. Systems to be unstable while all the coefficients are positive. Why this is unstable? Ha 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 ha. Okay, okay. Right. So sometimes higher order polynomials. For example, this s power 4 more than s power 3 times x power 3 also. We have fixed that, or you are looking for a condition that all coefficients are positive, right? When all coefficients are positive, we label that system as stable for now. But they have given with a special case where even though all the coefficients are positive, if you find the roots of that equation, the one lies in the left of, another lies in the right of. So even with this ratios, for example, why we are finding this ratios in the sense, what just to find the signs. For example, we will divide all the second or all other polynomials with the higher order polynomials, just to see whether there is any sign change between them, and we do a summation for all these things. If it change from positive to negative, similar to this, just when we are looking for all the sign change here, we can do, it's another method, just it is another method, there is nothing fancy here. So depending on the criteria, whether we are looking for all the coefficients are positive, that is not enough. So they are counter proving there can be some cases where all the coefficients are positive, but when you find the roots, there might be one roots lying on the right of, another root lying of the left of. So this condition is not sufficient. This is good for most of the problems, but not sufficient to prove all the problems. So that's why we are going for the Routh criteria. So in this Routh criteria, you cannot loosen this. Like, Routh criteria will let you know that there will be sign change when doing these operations.
Okay, so the ratio that we are calculating, like an minus 1 upon an, this is
Mm-hmm.
just dividing the coefficient by first coefficient to
Yeah,
see the sign.
by the higher order polynomial. All other polynomials coefficients by higher order polynomials and taking a summation of it. Right. Now I will see if we could solve one or two problems that tells you the difficulty of that other cases, special cases. Get to know more about it. So this is an important topic for exams, and expect one or two questions from this topic. So please prepare this properly. I'm taking the question. Okay, it will be in assignment 4. Right. Okay. I'm going to start with some difficult problem so that you can solve some easy problems based on that. Mm. Okay. This plus minus k, that is the controller. Another summation 1 by s into s minus 2 into s plus 3. So this is also present. Then y of s. There is an inner loop which is also a negative feedback, but instead of 1, it has a feedback of s. Good. Little complex problem. Then there is an outer loop that has only negative feedback. The question is, anybody told anything? Anyone told anything? I couldn't see. All right. Okay.
Yeah.
Yeah. Okay. Right. The question is, find the range of k for stability. Okay. This is the question. Right. There are. This question is seem to be little complex because there are two loops. You have to solve those loops to find the final closed loop transfer function. So let me solve that first. You try to solve it with me. The first thing is the open loop transfer function g of s is 1 by s into s plus 2 plus s plus 3. So you have to find the closed loop transfer function with this s first. If I try to,
Plus is not in between s plus 2 and s plus 3.
oh, okay. Oh, right, right. Okay, good. Thanks. Now we are trying to close this loop first, then we are trying to close the outer loop. So for closing this loop, I'm taking it as g of s divided by g of s into h dash of s. I'm calling this as h dash of s. This is h of s. That's one is h of s. There will be some one considering. Okay, this will give you 1 by again s into s plus 2 plus s plus 3 plus 1. Why am I writing like this? S plus 3 plus 1. Then again this will become s plus 5s plus 6 square. This will become s cube s square s when multiplied with s plus 1. Right or wrong? I have not missed anything, right? S square plus ys plus 6 into s plus 1. This will become. So when you come to the outer loop, there is a k. Am I missing a? Oh,
No,
okay, okay.
no,
So
won't it
yeah,
be
yeah. Yeah, yeah. The h of s is not 1 here, right? I cannot use this. Right, right, right. Understood, understood. So this will become, I will just write straight away. Divided by 1 plus 1 by s into s plus 2 into s plus 3 into s, right? So this will come there. S the same. S cube plus 5s square plus 6s plus 1s will be there. So this will give you s cube plus 5s square plus 7s. Right? I think that I'm correct now. Good. Now we have closed one loop. This will give you something like this. R of s plus minus k I'm writing this again because some people can get confused with this. So start visualizing like this. Once you practice, you will be able to do without this. Right? Good. So this is how our outer loop will look like. So once we solve those inner loop, you don't have any summation here. It will be just straight. Good. Now if we find the final closed loop system, this will become CFS by RFS is equal to K by S cube plus 5S square plus 7S divided by S cube plus 5S square plus 7S plus K. Good. So this is our closed loop transfer function. Now we are going to find the stability for the system. The question is find the range of K for stability. If the system has to be stable, what are all the range of K we can choose so that the system is stable. So the characteristic equation here can be written as SQ plus 5S square plus 7S plus K. Okay. Now writing in terms of Routh-Hurwitz criterion. So S cube comes first, S square, S1, S power 4. Until this, I have to write the table. First, writing the coefficients of the odd degree polynomials 1, 7, nothing else, right? Then writing the coefficients of even degree polynomials 5 and k. Now we are going to do the multiplication operation. That is 5 into 7 minus 1 into k divided by 5. So this will give you 12 minus k by 5. Oh,
35.
35. Okay, 35 minus k by 5. Silly mistakes. 35 minus k by 5. Then you don't have anything here, so you are just leaving this 0. Again 35 minus k by 5 into k minus 0 divided by 35 minus k by 5, right? This terms will be cancelled. So you will left with only k. Now, instead of the system to be stable, there should not be any sign change, no sign change. So you have to make sure 35 minus k by 5 should be greater than 0 and k should also be greater than 0. Right? Now, what conditions will satisfy this? 35 minus k greater than 0, 35 greater than k. So k should be less than 35, right? This
Yes.
is one condition. Then k should be greater than 0. So the range of stability will be 0 less than k less than 35. Make sense?
So, ma'am,
Yes,
what
ma'am.
was the use for inner loop that we calculated?
What was the loop for the?
The inner loop that we calculated, what was the use for that?
No, no, not like loop. Sorry, use. It's we have to ultimately find the closed loop transfer function. This system is little complicated with inner loop. So for solving the inner loop first, then solving the outer loop will help you instead of writing it all together. You can do that also. It doesn't. It doesn't mean that you cannot. But first solving the inner loop and writing it as a separate transfer function, then using the transfer function, consider that as a g dash of s and do solve the outer loop. This will give you a proper closed loop transfer function without any mistakes. Human error made mistakes.
Yes.
Right. So this is the range of stability we can find using this Routh-Horvitz criterion. These are straight away method there. It doesn't involve any special case right here, right? So we can look for problems that involves special case. Mm, sensitivity are also like this. Okay, 11th question can be like that. Okay, let me solve this. I'm just guessing that this will give you special case. If not, we'll look for another problem. I don't have solution for this. S into A square plus QES plus P. Okay, right. Now, if you want to solve this, this will give you 4 by SQ plus 9 S square plus PS, right? So the characteristic equation would be
S cube 9x squared plus x.
PS equal to 0. So this will give you 1 P 9 0. So this will become 9P minus 0 by 9 is equal to P square S1 S power 0 will give you 0 minus 0 0. Oh, here. It's a case 2 because there will be only one, but that one element is also 0. You cannot consider this under case 1 because always S0 row will have only one element, right? So here that one element becomes 0. So you have to consider this as a case 1 because there is nothing you can consider epsilon and the sign change, because if you replace this 0 by epsilon, how will you take whether it is positive or negative? You are only considering that, right? So consider this as a second case and solve with the auxiliary equation for this. How will you find the auxiliary equation for this? Mm, uh, written properly, right? Okay, okay. Sorry. Uh, we missed this. Missed to find the closed loop transfer function, right? It's g of s. Good. Please let me know if you made any mistakes like this. Okay, 4 by s cube plus 9s square plus ps plus. Now you will get the characteristic equation for this because the stability of a system depends on the closed loop equation. S cube 1 p a square will be 9 4. Now if you find 9p, this is q qp minus 4 divided by q. We don't know what is q and p, so I'm writing as it is 0. Again this will be qp minus 4 by q into 4 minus 0 divided by the same thing. This will be over. This is not a special case. Say here you have to depend on the value of q and p to find whether it is stable or not. Okay, I can introduce a problem here. Okay, please give me a time, one minute. Good, I have found one problem with special case. Ninth question. So they have given this characteristic equation of the closed loop system. straight. So we have to just start with this s power 5. Can you start solve along with me so that you will know where you are making mistake? If I made mistake, you will also be able to tell. 3681s plus 162 equal to 0. So this is the characteristic equation. S power 5 plus 2s power 4 plus 18s cube plus 36s square plus 81s plus 162 equal to 0. Right. Now we will solve this. The equation would be s power 5. We will start with s power 5 1, 18, 81. Then s power 4. This will be 2, 36, 162. Right. Now this will be 2 into 18, that is 36 minus 36 divided by 2. This will make it 0. Good. First column went to 0. The second 36 into 81 minus 18 into 162. This will give me
Then it will be 162 into 1.
no.
We take first column, I think.
Yeah, sorry, for this and this, right? Yeah, 162 into 1, 1. Correct. 36 into 81 minus 162 into 1. Then this will give you again 162. 36 into 81 will be 162. That will give you 0. This is also 0. There is nothing to multiply. So this will raise the case 2 problem, right? So then we are writing an auxiliary equation for this. Auxiliary equation with respect to the previous rows. That is 2s power 4 plus 36s square plus 162s power 0 equal to 0. So this is A. Considering this as some random name, A I am taken. So this will be di by ds, differentiating it with respect to the s. 8s power 3 plus 36 72s plus 0 equal to 0. Okay. You will be left with this. So now replacing the rows with the above equation. That is, I'm going to write it again. S power 5 1 18 81 2 36 162 8 72 0. Right. Now we are doing the equation again. 8 into 36. Can you tell me what this is? 2 into 72 divided by 8. If you have calculator handy.
16.
16. Okay, let me calculate. 8 into 36 minus 2 into 72. Mm. Okay. I'm repeating that parenthesis. Divided by 8. This will give you 18. Good. Now again finding 72 into 162. Again this will be 0 divided by 72. If we
Now
calculate
it will
that.
be 8 into 162. Again, we'll take first column.
Okay, sorry. I'm been confusing it with that. Okay. 162 by 0, again divided by the same number, then it will give you the same 162, right? Good. Now, this is s power 4, s power 3, s square, and finding the s power 1. If I do this 18 into 72, 8 into 162 divided by 18. Again it gives you 0 because this multiplies to same number. Then there are two zeros here, 0, 0, So again, we end up the special case 2, replacing it with the auxiliary equation 2. I'm considering this as A bar in order to reduce the confusion. It will be S 18S square plus 162 0, right? Equal to 0. Differentiating dA bar by ds is equal to 36 years. That only 36 years you will get. Now again replacing the same with this. $36. Good. Now 0 0. Now it should calculate 36 into 162 minus, okay, by 36. This will give you 162. Oh, good. We end up in the last s power 1 with only one element. So is there any sign change here? No sign change, right? So the system is stable. If there is even one sign change, then the system is pronounced to be unstable. Okay. Okay. I think I'm not in the right mind. I'm missing so much today. So since we use the auxiliary equation, the stability will be depend on the auxiliary equation only, right? It should not depend on the sign change of the original system. So the auxiliary equation, when you found the first one, the last one, that is 18s square plus 162. We'll look with the first one only. This equation, 2s power 4 plus 36s square plus 162 equal to 0. Okay. If you look this, again, since this is easy to calculate because these two terms are missing, right? There is no terms about of the odd equations. So when there is this missing term, it will always have a root in the imaginary axis. So when you solve this, you will get a pole pairs. Since it is a 4 power 4, you will get some a. If you calculate using this, you will get it plus or minus ag plus or minus same aj. You will get like repeated poles because the inner term is missing. So this will not give you a plus bj, only aj or bj you will get. So and the order of the polynomial is higher. So if the number of roots is equal to the your higher order polynomial, so since it is 4, you will get 4 roots at the imaginary axis.
I didn't get like how is it imaginary? How are we finding it?
Same when you find the roots of the polynomial equation, since it will take time, I'm not doing it. So when you do this and look for the poles, you will have only the same equation on. For example, we will start with -1 and look whether this satisfies. Otherwise, we will change it to 2. So similarly, we will find the roots for this higher order polynomials, right? Root 3, root 4. So if you do that, you will get the roots of this equation. I'm telling that because there is a missing orders in between. It will always end up in a imaginary axis. Like there will not be any roots like this. You will have a roots only like this, only imaginary term, not any real part. So since the order of polynomial is higher, I'm telling this will be repeated. Since it is repeated, the system is unstable. Right, we cannot comment on the system based on the sign change since we use the auxiliary equation. We have to look for the nature of the auxiliary equation and we have to comment on it. It is a unstable system since we have repeated poles on the same location.
By just looking at this equation, how did you find that it will be imaginary? For sure.
If you look, I'm writing it in color. See, s power 4 plus 36 square plus 162 equal to 0. Right? When you try to find the equation for this, it is supposed to look like this, right?
Yes.
Ah, when you put the, for example, if you use -3, I'm starting off with -3. This will give you, how will you consider this? -3, this will be -1, 3, some 39 something will come, and 3 into 39, 162, right? 12, 142, 142 minus, this will give you 20. So this doesn't work. So when you do, when you change this again and again, since there is two missing term always, so you will have an roots that are like this, minus j or -2j or -5j. You won't, like, by practice I'm saying, you won't get anything like 1 plus 5j. You won't get like 2 plus 3j. There won't be any real plus imaginary. If you solve it and see, you will get always in the equation that looks with two coefficients in between, that even order or odd order or missing. You will get a roots like this only. Sorry, like this. Only imaginary part only you will get. That's how I'm saying. You will have an imaginary root, always imaginary roots. But since the equation has higher order polynomial, the imaginary roots will be higher. So 4 imaginary roots will be there. You will get the same roots again, again. You can cross check this with MATLAB also. Again, test. I'll
Yes.
just test and let you know what are all the exact roots of this. I'm opening the MATLAB.
Just a question. When
Uh,
will we get the MATLAB exercises?
okay, I think it will be in within 2 weeks. Or maybe after quiz 2. We have to check with the professor. Because quiz 2 is approaching so quickly, right? August 3 is your quiz 2.
This one.
Yeah. So I think after that only. Okay. Mm, this is transfer function equal to how will you write this transfer function? Roots for this you have to find, right? Good. Df equal to df of 1 comma, this is 2 0 36 0 162. Roots of, or it is pole of df2. Good. I will just show you in the camera how we can find this. Okay, I cannot use camera while sharing the screen. Okay, it's the roots. The MATLAB gave us -3j minus 3j plus 3j plus 3j. So there are two repeated rules at the plus or minus 3j. That's what it is giving. I can share you some simple step for finding this. Like you are finding it difficult to find the roots by hand, right? Okay.
Yes, ma'am.
I will tell you. Just see if this is x power 4, finding this is possible, but this will take a longer time, right? So the easy step is to equal to 0. Replace this s power 4 with s power 2 or some other a power 2. So write this in terms of square so that you can find this easily. So a square will be some. So if I am taking a equal to a square, then this will be a square. This will be a plus 162 equal to 0. Right? Now can you solve minus b plus or minus
Yes.
root of b square minus 4ac divided by 2a. This will give you minus 36 plus or minus root of 36 square minus 4 into 2 into 162 divided by 2 4. So this will give me minus 36 plus or minus what is 36 square? If you can find it before me, please tell me. It's very difficult to use in this computer. 36 into 36 minus 8 into 162. 0. Is it giving 0? Is it right? Can anyone
Yes,
confirm?
yes, ma'am.
It's
Yes,
0,
ma'am.
right?
It's coming zero.
Okay. Then this will become only this. It will give you minus 9, right? So you are solving for a, so your a is minus 9. Now you back substitute a equal to a square, whatever value you got. So you got x is a equal to minus 9. So substitute s square is equal to minus 9. So you will get s is equal to plus or minus 9 root 9. This will give you plus or minus. Since it is a minus, sorry, s is equal to root of minus 9. This will give you plus or minus 3i or 3j, whatever you want. So similarly, since you consider s square as a, for each, this is for one a. Similarly, for s square 2 roots, you will get another pole pair similar to this. So always this will be a repeated roots when you are one of two of your coefficients missing in between. This will be plus or minus 3j twice. Clear? Any doubt in
Yes,
this?
ma'am. Yes, ma'am. Okay.
Okay, right. You can find the coefficient of the roots like this. Okay, I think, yeah, that's what I wanted to discuss today. If you have any doubts in this, I can summarize once again for those who are watching it online. So we have found we have studied the Roth-Hurwitz criterion today. It's very important in terms of example. You can expect one or two questions maximum from this content. The first thing is you have to find the system stability. The stability depends on whether there is any sign change or not. No sign change will be stable. Number of sign change, number of poles in right half of the S-plane. They won't ask how many poles are there in left half of the S-plane. If there is no sign change, the higher the order of the polynomial, that many poles are in the left half of the S-plane. That doesn't make any sense. They won't ask that. If any question is there, the system must be unstable, and they will ask how many poles are in the right half of the S-plane. So for that, you can use this criteria also. The second thing is case 1, where one or the first element of column goes to 0. So for this, replace 0 with a small value epsilon and proceed with the same steps and look for any sign change. And for case 2, all elements goes to 0. So in that case, look or consider coefficients of above equation where it went 0. Then take that as an auxiliary equation, equate it to 0. Then differentiate it with respect to S, and you will get a equation. Replace this the tables row. Okay, and proceed with the step. Now the important point here is you should not look for sign change. I myself made a mistake here. Check the roots of the auxiliary equation. If there is one pole pair on imaginary axis, then the system is marginally stable. It won't affect the stability unless it is pushed otherwise. If there are more than one pole pair, the system is unstable because this extra pole pairs can increase the oscillations and push the system to the verge of instability. Right? I think this is fine. I hope this is clear.
Yes, ma'am. It's clear.
Okay, good. If you have any doubt, you can ask. Otherwise, you can wind up the session. The next class, we can start off with the root locus problems.
Yes, ma'am.
Right. Good. Thanks.
Thank you.
Thank you.